Okay, so this is the second part of section 2.2 on page 14, about halfway down. We're going to talk about infinite limits as x approaches a particular number. So that as you approach a value, like we talked about in section 2.1, but instead of getting another answer, that the limit is actually going to be infinity. So if the values of a function f of x outgrow all positive bounds as x approaches a finite number a, we say the limit of f of x as x approaches a, not infinity, as x approaches a, is infinity. And then if the values of f become large and negative, exceeding all negative bounds as x approaches a number a, we say that the limit of f of x as x approaches a is negative infinity. So if we were to look back at our function, our 1 over x, so that's just our good old-fashioned hyperbola. So if I were to just graph a hyperbola, and I were to think about the limit as I approach 0 from the right. So that means the limit at 0, I'm approaching from the right, heading towards 0, so basically heading to the left. What ends up happening? So as I approach 0, from the right, heading towards the left, my y values start getting bigger, 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 up forever. So then that's outgrowing all positive bounds, right? It's going up forever. We say that limit is infinity. And as I approach 0 from the left, so as I'm starting from the left, heading towards 0, my y values are getting smaller, 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 approaching negative infinity. So basically, as you're approaching a particular value, you're shooting up or down or both down. We say that that line is a vertical asymptote. So basically, if you have, a limit as you approach infinity or negative infinity, that's giving you a horizontal asymptote. But if you approach a particular value and the limit is either positive or negative infinity, then that line is a vertical asymptote. So that's what this is saying here. And again, that's an or. It could be either of those cases. It gives you a line. A vertical line is your vertical asymptote. All right, so then find the vertical asymptotes for each function, then describe the behavior to the left and to the right of each vertical asymptote. So if we were to graph, so take a second, go ahead and graph it, pause this if you need to. Here's my graph of 1 over x squared. So this is asking me for two things. So where do I have a vertical asymptotes? It could be more than one. In this case, I only have one, and x equals 0. And then it's asking for what is the behavior to the right and to the left of that vertical asymptote. Okay, so if my vertical asymptote is at 0, then I want to find the limit as my function approaches 0 from the right and from the left. And if that's where I have a vertical asymptote, then my limit should always be infinity or negative infinity, one or the other. And so as I approach from the right, heading towards 0, my y values get bigger, 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 so the limit is infinity. Okay, as I approach 0 from the left, heading towards the right, my y values get bigger, 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 so my limit is infinity. So both of those happen to be infinity. Okay, so now here's the graph for the next one. So you might want to pause, take a look at the graph yourself, think about, okay, where are my vertical asymptotes? And then what are the limits to the left and the right? So if you're watching this on your own at home, you might want to pause right now, think about that on your own, and then watch the video and confirm if you have it correct or not. All right, so it looks like I have 2 vertical asymptotes. I could actually also know that because I know from before about continuity, if I factor whatever gives me my denominator of 0, that's where I'm going to have my vertical asymptotes, my discontinuities. So here I have a vertical asymptote 2 places. I have one at -2 and I have another one at 2. And so again, I want to give the behavior to the left and to the right of the -2 and the 2. So as x approaches -2 from the left and as x approaches -2 from the right. So you got to be careful with this notation here. Okay, so here's my -2. As I'm approaching, I have this first from the left. So as I'm approaching from the left, so here's the left. As I get closer to -2, my y values are going down, 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 down. This is going to be negative infinity. as I approach -2 from the right. So it starts here, I know it goes down, but then it picks up. As I'm getting closer to the 2, my y values are shooting up, so that's infinity. Okay, and then I'm going to think the same way over here as I'm getting closer to the 2. So first from the left, I know it goes down and then it comes back up, and then, but as I'm getting closer to the 2, the y values are going up from the left. Oops, I put that here this time. I don't know why I switched. Ooh, did I switch these? Shoot, we'll come back to that. Okay, so from the left, it's going up, and over here, as we approach from the right, it's going down. All right, let's look at this. I think I had these backwards when I was thinking about them. So again, here, from when I said from the left, it was going towards -infinity. Okay, these are just flipped around. All right, sorry if I screwed you up there. Okay. All right, so that's vertical asymptotes. Now the next thing, end behavior models. So sometimes when I am looking at these, I have this polynomial, right? And the end behavior, if I graph that, it might look just really, really complicated. Okay, so here, right now, this is my graph of this whole function. I want to know what happens to this as x gets really, really big and really, really small. So this is back to end behavior. So this is the graph of this f of x, and I want the limit of f of x as, again, x equals or approaches infinity, and as f of x approaches -infinity. And so what mathematicians realized was that instead of having to graph this whole thing, the end behavior of this was the same as the end behavior of this much simpler function, really just the leading term. Okay, so they would have way different answers, like if you compare them in a table, but the end behavior is the same. Okay, so here is the, 3x to the 4th minus 2x cubed plus 3x squared minus 5x and so on. Let me turn on the graph for just this 3x to the 4th. And I just want you to see the end behavior of them are the same. So the green one is the original, and then this is just the leading term. So I know the graphs are a lot different, but you see that the end behavior is the same. So as we go towards -infinity, they both shoot up. As we go to positive infinity, they both shoot up. And so mathematicians use this because instead of having to know what that looks like exactly and where are all the terms, if they were just interested in end behavior, they could just focus in on the leading term. And so that's what this definition here tells us. Wait, no, that's not what I want. So, right here is what I'm talking about. So if you have a polynomial, the end behavior of that whole polynomial is the same as the end behavior of the leading term. Okay, so that idea right here goes up here with this. So the end behavior of the whole polynomial is the same as the end behavior of the leading term. Now some functions might have different kind of end behaviors. So if we look, well, take that back. Let's take a look at this one here. So it says find the end behavior model for this whole thing. So because this is rational, it's like the end behavior of a polynomial over a polynomial. So what we can do is say the end behavior of this whole thing can be modeled by the end behavior of the leading term for the numerator and the denominator. So our end behavior model would be, I'm going to take the leading term for this one and the leading term for this one and divide them. So my end behavior model will be 2/3 x to the 3rd. And so if I were to graph this, so here's the graph of that whole big thing, right? The whole big thing. Again, mathematicians didn't have graphing calculators back in the day. That was a pain in the butt for them to be able to graph. And so what they focused in on instead was just the end behavior of, again, the leading coefficients, the leading terms. And so see how if I graph right? This one, it's got the same end behavior. So that means that we could say the limit of f of x as x approaches infinity is as x approaches infinity, y is approaching infinity, and the limit of f of x as x approaches negative infinity, as x gets smaller, y gets smaller, is negative infinity. And that can be based just off of this. So what that means is for this one, I don't need to graph that whole thing because I have no idea what the heck that thing looks like. I don't have to graph that whole thing. The end behavior of this is going to be the same as the end behavior of its end behavior model, which I'm going to call it h of x, so it's a different letter. It's just going to be taking the leading terms of each of the numerator and denominator. Okay, that's just h of x equals, up those cancel, so 2/5, that's just the horizontal line through 2/5. So what that means is that this has a horizontal asymptote at 2/5. So as x approaches really positive or negative infinity, the limit is going to be 2/5. Okay, and we could see that. Here I have it graphed. Sorry, there's a terrible glare there. Let's see. Okay. So here is the whole big thing, right? It seems like it's leveling off. And then I just want to show you if we were to also graph just the 2/5. There it is. Let me turn this on so you can see it. Okay, so you can see that they have the same end behavior. There's the 2/5, and you can see the original had the horizontal asymptote. So again, you don't have to, graph this whole thing. You could just use the end behavior model. And that's what mathematicians did when they did not have fancy graphing calculators to do that for them. Now, some functions, like the funky ones, like ones that aren't polynomials or rational, don't always have something nice and straightforward like this. And so up here we have this definition for an end behavior model. So a function g is a right end behavior model for f if and only if the limit of that quotient of f of x and g of x is equal to 1. And something is a left end behavior model if and only if the limit is x approaches negative infinity of f of x over g of x equals 1. So in example 8, they gave you a function and they're saying g of x is a right end behavior model and h of x is a left end behavior model. Okay, and it's asking us to confirm that it's true. So to confirm that it's true, if it's a right end behavior model, it's that you have to show that the limit of f of x over g of x as x approaches infinity is 1. So basically that means that we need to show that the limit of f of x, which is this whole thing, divided by the limit of g of x, which is this x right here, which they said was the behavior model, as x approaches infinity, we have to show that that equals 1. And so the idea is that if we were to split this, right, and rewrite this as the limit of x over x plus the limit of e to the negative x over x, that limit should be 1. Okay, well this right here is just equal to 1, right? That just equals 1. So that's 1 plus, then what you would do is you would graph that, right? So if we were to graph this right here and look at the graph, the limit of this is 0, and if you add those together, that equals 1, which is what we were trying to show. Okay, and then it would be the same idea here for the left end behavior model. So we would have to show that the limit of f of x over g of x as x now approaches negative infinity is 1. So we would be showing as x approaches infinity that x plus e to the negative x over, now it's the e to the negative x, that equals 1. Okay, so then we would just go through the same process. I meant to make this say a limit, but this is what we're trying to show. Okay, so then we would have the limit as x approaches infinity of x over e to the negative x plus the limit, this is a negative infinity, as x approaches negative infinity of e to the negative x over e to the negative x. Okay, well that's going to be a 1. This, if you graph, guess what? Equals 0. Go ahead, pause, look at the graph, notice it does equal 0, which equals 1, and that's what you were trying to show. Okay, and let me just show you too, if we were to graph, so if I just graph the whole thing, so this is the graph x plus e to the x. So if I wanted to know the end behavior of this. So again, mathematicians did not have these fancy calculators, so what they would do is they would try to figure out ways to figure this out by other means. All right, where did I put it? Here it is here. Okay, so there it is. All right, so now let me just show you. If we just, so it said that e to the x, or x was a right end behavior model. So let's say I just graphed this line, y equals x. Okay, notice, to the right, do you see how these both have the same end behavior? That's why that's the right end behavior model. All right, now if I turn on this e to the negative x, look what happens. See how these have the same left end behavior. That's why we can say that's a left end behavior model. All right, and then the last thing, seeing limits as x approaches infinity. So another thing that mathematicians figured out, just because again they didn't have graphing calculators, they had to figure out other patterns for figuring out limits sometimes, is we can investigate the graph of y equals f of x as x approaches positive infinity by investigating the graph of y equals f of 1 over x as x approaches 0. So if I rethink of this as the limit as x approaches 0 of f of 1 over x, which means that in place of 1 over x, in place of x, I put in 1 over x. That becomes the limit as x approaches 0 of the sine of x. And if you think about the graph for the sine of x, as x approaches 0, it's getting closer to 0. So that would be our limit. So that was just a workaround. All right, and so then this would be the same thing here. Instead of thinking of it as x approaches infinity, I could think of it as the limit of 0 and then of f of 1 over x. So in place of these x's, I'm going to type in, or I'm going to put in 1 over x. So then that would be the limit as x approaches 0 of 1 over x times that would be cosine of x. Okay, and then the limit, if you think about your cosine graph, that was the guy that went like that. So as you approach 0, the limit here is 1. And so you kind of think of this, the limit of this, right? As we approach infinity, we know, or as we approach 0, we know is infinity. The limit of this is 1. So overall, we would say the limit is infinity.